Hello and welcome to our talk. I am Megha from Albert Einstein Institute in Hannover, and I am jointly presenting our work on IfoCAD simulations for TTL noise analysis in LISA with my colleague Rodrigo. Quick introduction to TTL noise, that stands for tilt-to-length noise, which is a coupling of angular or lateral jitters of LISA spacecraft with alignment errors of the optical components and the imperfections of the beam wavefront leaking into the interferometric readout signal. Could be of two forms: geometric coupling, which is related to direct change in the optical path length of the beam, and non-geometric coupling, when there is no actual change in the optical path length of the beam, but the signal is solely affected by the imperfections of the beam wavefront. For highly sensitive interferometers like LISA, it could be an overwhelming noise and therefore needs to be carefully computed in order to be able to suppress it for the precision requirement. For that, TTL noise in LISA is modeled as a linear function of angular and lateral degree of freedom, where the associated coupling coefficients, they determine how strong the coupling would be in a particular degree of freedom for various optical effects. We here simulate the LISA dedicated optical setup to examine the TTL noise sensitivity to the alignment of the optical components to compute the coupling coefficients due to the alignment errors and the effects of the wavefront. We compare the sensitivity of TTL for two different types of signal definitions. TTL is valid for both interferometers in LISA, the test mass interferometer that reads out the position of the test mass with respect to the local optical bench by sensing an interference of a Gaussian beam with another Gaussian beam. And it is there also for intersatellite interferometer, or what we call as long arm interferometer, that senses the distance variations of the two spacecraft in the LISA constellation by having an interference of a local Gaussian beam with a beam that is received from far spacecraft and that gets clipped on the receiving aperture of the telescope and hence takes a form of a diffracted top hat beam. Due to diffraction being involved, the TTL computations for long arm interferometer, they are a bit more complicated than the computations of the test mass interferometer. For our TTL simulations, we use our software library IfoCAD that was developed at AEI, and it is a useful tool for designing optical layouts of high precision interferometers and computing different interferometric signals. If you want to know more about it, you can visit our website, which is provided here on the slide. With IfoCAD, we have a model implementation for phase 0 LISA optical bench with all the components aligned according to the nominal parameters. And we also have implemented the dedicated imaging systems for the two interferometers to reduce the geometric counterpart of the TTL contribution. And the image shown here is the 3D image of the setup that we have been using in our simulations. Here is the optical bench with all the components aligned terminally, and there is a freely floating test mass. There is also an assembly of the telescope aligned on top of the optical bench, which is made of aspheric mirrors based on the design delivered by NASA. So far, our IfoCAD viewer has not been adapted to display the real aspheric objects for the real aspheric mirrors that are used in the telescope, and therefore this structure here has the dummy objects from the IfoCAD viewer just to show the spots where the telescope mirrors would be. Whereas in our simulations, we actually have used the aspheric surfaces for the mirrors. For the TTL computations of long arm interferometer, where we also needed to simulate the diffracted top hat beam, which is a non-Gaussian beam type and not very trivial to propagate. For that, we have two alternatives of decomposition methods. One can either decompose such a non-Gaussian beam wavefront into higher order Gaussian modes or on the grid of fundamental Gaussian beam. With the key method at hand and this preliminary optical bench setup for LISA in IfoCAD, we have computed dedicated simulations to compute TTL contributions from various sources for the test mass and long arm interferometer individually. We also have used highly simplified version of this setup dependent on the case study to reduce the computation time and effort. Although on LISA optical bench, in reality every component would be aligned with ultra high precision, but there are associated tolerances which are needed to be factored in because of the fact that even a small amount of alignment error can generate some significant amount of contributions to TTL noise in the signal, and that are needed to be investigated. For instance, the alignment tolerance of the beam, the error in the alignment of the detector, the effects generated due to wavefront, the noise brought by the imaging systems due to their imperfections, and the position of the offset of the center of tilt of the spacecraft with respect to the nominal optic axis on the optical bench. These are several optical effects that the coupling is sensitive to and needed to be computed carefully to estimate the coupling coefficients, and we have examined such optical effects individually for their noise contributions for each interferometer separately by injecting one effect at a time, and we computed the associated coupling coefficients that we have and we summarized our results in our technical note, which is internally available for the LISA consortium members. In the course of our investigations, we have found two types of coupling behavior. The first order coupling behavior, where the fit coefficient to the curve is the TTL coupling coefficient for that particular effect for the linear model that I have shown few slides back. Whereas for the second order coupling behavior, due to the fact that the angular jitters are going to be very small, this response to the signal can be conveniently linearized about a particular constant angular offset within this tilt range to extract the coupling coefficient for the linear model. So far we have talked about the effects generated due to the angular jitters of the spacecraft with the alignment errors, but we also have computed the effects of jitters of the spacecraft and lateral degree of freedom for the tilted test mass in the test mass interferometer, that is called as the lateral jitter coupling. As final results, we found out that for the test mass interferometer, the total contributions from the angular jitters in TTL noise in root sum square for all the effects that we have computed is around 100 micrometer per radian. And for the long arm interferometer, the angular jitter contribution is approximately 8 millimeter per radian. The lateral jitter coupling for the test mass interferometer case is approximately 60 micrometer per meter, whereas we have not yet fully investigated the lateral jitter coupling contributions for the long arm interferometer, which we also anticipate is not going to be too significant. So far what we have investigated here are the preliminary results from the preliminary optical bench setup implemented in IfoCAD without any realignment for compensating the TTL, which could bring down the numbers to the lower side, because our aim was to investigate the TTL effects from a multitude of sources for the implemented model. This model will be adapted according to the new upcoming designs and will be evolving in time. We also are working on few more things like computing TTL effects at far field and testing the cancellation of TTL noise between the test mass and long arm interferometer from some specific sources. That was on my part. Thank you so much for your attention. If you have any questions, then drop them in the comment section. And now over to my colleague Rodrigo.
Thank you, Megha. I will continue now with the second part of this talk. This part concerns the ongoing work with tilted-length coupling noise characterization of LISA interferometers as currently designed using IfoCAD. The main objective of this work is to create a model of the new LISA design in IfoCAD, where the geometric tilted-length coupling can be simulated. This includes changes to the telescope and optical bench designs. By creating this IfoCAD model and the corresponding simulations, the intention is to further facilitate IfoCAD simulations for future adaptations to the LISA design. As Megha has already introduced, there is a working IfoCAD model of the phase 0 LISA interferometers, pictured here on the right, which can ray trace through the components in simulating heterodyne interferometry in LISA. This includes simulations of geometric tilted-length coupling as observed by the quadrant photodiodes in the long arm and test mass interferometers. The simulations currently use Gaussian beams only. These IfoCAD simulations are a holistic approach to the tilt-to-length coupling characterization of LISA interferometry. These components on the optical bench and telescope are included to simulate optical path length signals and differential wavefront sensing on the quadrant photodiodes of the respective interferometers. The performance of LISA is affected by the alignment of the components, and misalignment couples into the various interferometer channels, causing static misalignment of the test masses in flight, which then results in the additional noise. These effects cannot be fully investigated experimentally on the ground before the mission. Therefore, the simulations are necessary in order to predict the amount of cross-coupling between the heterodyne signals and find critical components that are the main contributors to resulting tilt-to-length noise. All components are to be subjected to randomized misalignments with realistic boundaries in Monte Carlo simulations. Then we can obtain tilt-to-length coupling noise budget of jitters of the telescope, optical bench, and the test mass respectively. Furthermore, a drag-free and attitude control system, DFACS-like control system, will be implemented to be able to create time series analysis of the optical path lengths and DWS measured on the QPDs. DFACS is a dynamic feedback control scheme that is to log the spacecraft motion, longitudinal and angularly, to the test masses on board. The DFACS control, as implemented inside of IfoCAD simulations of the LISA model, will consist of 3 nested loops. The innermost loop will contain the test mass rotation control, which corresponds to the DWS measured by the test mass interferometer. Secondly, the spacecraft will rotate to minimize the DWS on the long arm interferometer. Finally, the spacecraft is translated longitudinally to a reference position with respect to the test mass. The phase 0 design of LISA is currently modeled in IfoCAD and is represented in a simplified fashion on the image to the right. This is also the nominal position of the components, where if any jitter were introduced, say in the test mass interferometer, it would introduce a noise contribution to the measured signal, simulated signal, that is. In reality, all the components will contain misalignments with respect to the inertial frame, which is what DFACS is supposed to be reducing. And this is being done in a fashion such as first rotating the test mass itself, such that the DWS on the test mass interferometer reaches 0. Next, the spacecraft is aligned by rotating it such that the long arm interferometer is minimized. You will note that this actually makes the test mass misalign with respect to the spacecraft again, but that being in the center of, in the middle of the nested loop, that is being done concurrently. Finally, the spacecraft is moved to a reference position with respect to the test mass. Currently, it is the only longitudinal axis that is of interest, but it is subject to change for future simulations. Also, spacecraft roll is not implemented yet, but this will be relevant in the future when simulating the entire spacecraft with 2 optical benches. With randomized static misalignments of the components and DFACS-like control, the geometric coupling introduced will be able to be characterized for the long arm and test mass interferometers as a whole within the IfoCAD environment. This project is still in the beginning stages, and it is currently utilizing the phase 0 design. The simulations will help to validate the tilt-to-length coupling budgets being derived independently by other simulations and analytically. Hopefully, these will assist in identifying critical points in the interferometers design with regards to tilt-to-length coupling noise. The plan is to implement the current changes to the LISA design and obtain full tilt-to-length noise estimations, hereby creating an IfoCAD model where future adaptations are more easily implemented to be used for future simulations. This can include changes to the imaging systems placed in front of the QPDs, for example, in both the interferometers. Analysis of the non-geometric tilt-to-length and flat-top beams will be introduced at a later juncture. More challenging yet, in the future, the IfoCAD model will be introducing the second instrument within the spacecraft, introducing many more degrees of freedom to this problem. This concludes our talk. If you have any queries, please do not hesitate to get in contact with either Megha or me. Thank you very much for your attention.